46, there's just a little bitty thing that I want to go over with you. And once I go over this with you, we're going to go to yesterday's homework and talk through some parts of it and make sure you kind of really got that solidified before you practice some more of these exact same problems tonight. So nothing really new except for one little bitty snippet of something I'm going to teach you right now. So page 46 in your packet to do the notes. So some of the questions that we're going to see today are going to ask you this. On average, how many do you expect to get? How many do you expect to get, whatever it's asking for? Okay, well, there's an option there. If they tell you, if you are told the number of trials that you are going to look at, for example, they say, out of 12 people, how many of them do you expect to be lefties? All right. Then you would use these two formulas on your formula chart. And they're kind of hard to see here, so I'll go through them. This is how many, on average, you expect. You multiply the number of trials you have times the probability of success that you are looking for. Okay, and then for the standard deviation of that, it's that formula, but we'll go ahead and go through that. It is the square root of the number of items that you have times the probability of that event, and then 1 minus p is the failure of that event. Okay, so again, if they tell you n, then you can find the mean and the standard deviation with those two formulas. So let's look at number 8. If I ask you how many drivers you would expect, I'm going to say something here, to wear a seatbelt. That's missing. It needs to have something in there like that. So if I ask you how many drivers you would expect to wear a seatbelt out of the first 10 cars that come to a traffic light. All right, so say you go down there to the traffic light at, I don't know, what's the one, Ranch House Road. Wait, not Ranch House Road, but what's the main street right here in front? Oh, Bailey Ranch, there you go. Okay, Bailey Ranch Road. So you go down there to the light, you sit there, and your friend is keeping tally, and you're going to tell him, you're going to say, okay, I'm going to count 10 cars, and I'm going to count how many of those ones are wearing their seatbelt. So you start counting, you're counting, you're counting, you're counting, and you see, on average then, when you do sets of 10, say you sit there and you count 10, you see how many of them were doing a seatbelt, wearing a seatbelt. Then you do another set of 10, see how many of those were wearing a seatbelt. Then you do another set of 10, and so on, and you sit there and you do that for an hour, and you see how many are wearing their seatbelts on average, about this many. So let's go ahead and compute it. Then so this is the average amount that you would expect to be wearing a seatbelt. The n is how many are you going to be looking at? 10. And the probability of wearing a seatbelt is 0.75. This is from the previous page. That had been told to us on the previous page, by the way. That the probability of wearing a seatbelt was 0.75. So the probability of not wearing a seatbelt, of course, is 0.25. All right, so that's data from yesterday. And so that is 7.5 drivers. Okay, 7.5 drivers. So why can this be a partial number? Because it's an average. You're sitting there all day long, or let's just say one set of 10 had 8 people wearing a seatbelt, another set of 10 had 7 people wearing a seatbelt. So on average, there was 7.5 people in those sets of 10 wearing seatbelts. All right, with what standard deviation? So the standard deviation of wearing a seatbelt would be, and follow this formula, square root of 10 times the probability of success times the probability of failure, and that comes out to 1.37 people. So essentially, if you sit there, you're going to get about 7.5 people plus or minus, 1 1/3. So would 6 people out of 10 be a unreasonable amount of people to be wearing a seatbelt? Would 6 be unreasonable? No. That's just a little over 1 standard deviation away. Would 9 be unreasonable? No, because 9 is just a little over 1 standard deviation away. Would 2 be unreasonable? Yes. 2 people would be quite a few standard deviations away from what I would expect to happen. All right. So now, the next thing is, though, what happens if you are not told how many people to look at? So if you do not know how many to look at, so you're not told, look at 10, you have something like this. How many cars would I expect to have to count until I find one driver that, in this case, is not wearing a seatbelt? So how many are you going to have to go? You're going to sit there and go, okay, wearing a seatbelt, wearing a seatbelt, wearing a seatbelt, wearing a seatbelt, wearing a seatbelt. Okay, there's not wearing a seatbelt. About on average, how many do I have to count until I find that one that wears a seatbelt? Yes, very good. Because, and you can kind of, I don't know, how did you think of that to come up with that? Who said that? Austin, you did? Okay, because it's a 25% chance, and this is not on the formula chart, so this is one that you have to kind of think about, but it's always 1 over P. 1 over the probability that that event will happen. So in this case, it was 1 over the probability of not wearing a seatbelt. So in this case, it is 4. Okay? Because 25% of the people you would expect to be wearing a seatbelt. So you're going to have to look at about 4 drivers to find one that's wearing a seatbelt on average. So, generally speaking, you would be going wearing one, wearing one, wearing one, not wearing one. This would be your one that you have that is not wearing a seatbelt on average. Done. And that one, by the way, does not have a standard deviation because you don't know what the N value is. You're going to have different amounts, okay? So let's go now to your assignment that you guys did last night. You did these day 1 problems. I want to check the ones that you did with you and fill in the blanks on the remaining ones. And you will get stamped on this. I'll probably end up stamping you on it tomorrow. Okay? But I will tell you, I don't always go through a lot of problems. I think these are ones where I think the wording is so subtle. You need that support of going through a lot of problems with me, piece by piece. I know when I did this unit, the first time I ever had to do it, I remember sitting there, I would do the problems, and then I would want to check the answer immediately to see if I was, thinking in the right direction. Okay? So you might be feeling that way, too. All right, so here we go. Let's see how you did. This is about the basketball player who makes 80% of his shots. They're independent of each other. So what's the probability that you miss for the first time? The first time you miss is on the 5th attempt. So what do we then know is happening? Is the order, okay, he made it on the 5th, but what about the order? Do I know exactly what's happening, or is it just kind of like, is that one somewhere in the 5 times? You specifically know the order, so you know in particular, or you know exactly what the order is. It's going to look just like that. Since it looks just like that, this was a geometric one, because you made it, and then you did not make it, and it's that probability. Now, I want to show you a little calculator trick. Here is another thing that you might prefer to do on your calculator instead of multiplying all that out by hand. Okay? Under second bars, just like how we had found our binomial PDF yesterday, there's geometric PDF. And so if you go to the bottom of the list, there's geometric PDF and geometric CDF, and I want PDF because particular person right there in the 5th spot. So in particular in the 5th spot. So I hit that and I go, all right, I just know the probability and where it wants to go. I don't in the 5th spot. So in this, you don't put NPK, you just put PK. So the miss, which is the 20%, needs to occur in the 5th spot. So 0.2, comma, 5, and then I hit enter, and there is my percentage of 0.08192. Okay? So you might like doing that, calculating that way. All right, next. Makes his first basket on the 4th try. So what's it saying? Exactly where that spot occurs, in particular where that goes. The order is known exactly. So, if I was to do this on a calculator, how would that look? Geometric PDF, and then what do I want to happen and when?
You want to make it, which is 80%.
Good. You want to make it, which is 80% on the 4th try. Oops, I didn't do that. And it's all on there. Okay, sorry. So, geometric PDF, I want to make it on the 4th try. And there it is, 0.64. Okay, so not very likely. You're going to be making it before the 4th try, probably. Okay, now, this one is different. You did not do this problem, so let's do this together. Here we go. So this is kind of like today's classwork / assignment that you do have to complete then to get your stamp. I'll probably stamp you tomorrow. Okay, he makes his first basket on one of the first 3 shots. Okay, so that is defining an order. The reality is that that is telling you where those should occur. So it's a geometric problem. It should occur on the 1st spot, or it should occur on the 2nd spot, or it should occur on the 3rd spot. Do you get that? Does that sound reasonable with what it says there? Okay. He makes his first basket on one of the first 3 shots. So it would look like this. Making it on the 1st shot, or, so then we would add to that, making it on the 2nd spot, or making it on the 3rd spot. Okay? And so then you can compute all of that separately, and you would come up with your answer. The calculator does give us another little thing to do this with, and it is called geometric CDF, because I'm going to do this accumulation, cumulative. I'm going to accumulate not only this landing in the 3rd spot, but I want it to land in the 2nd spot and the 1st spot as well. So I'm going to do geometric CDF, and I want that 80% to land in all the places up to and including the 3rd spot. Okay, geometric CDF, up to and including the 3rd spot. So here's how that's going to look. Okay, geometric CDF, he makes it up to and including the 3rd spot, and so that adds all of them together, 0.992. So there's a 99.2% chance that he's going to make it somewhere in those 3. And also, you can think of this as he's also going to make at least 1 shot. That's another way of thinking of this problem. Okay, and so we're going to kind of expand upon that later. But making at least 1 shot, because if he makes it here in the 1st, he could also make it in the 2nd and 3rd. I don't care. I'm just defining that he made it in the 1st. He makes it in the 2nd. He could have also made it in the 3rd. I'm not telling you. It's just, defining. So he makes it at least once. All right. So 0.992, so 99.2% chance that he makes his first basket on one of his first 3 shots. Okay. Next. Here we got the computer chips. Probability of a bad chip is 2%, and you guys did do the first one. The probability that the 5th chip is the first bad one that you find. So that was geometric because why? Why is it geometric? It's specifying the order, and it's specifying this order. They're good until the 5th one is bad. Okay, so you could put it into your calculator, geometric PDF, and the .02 occurs in the 5th spot. All right, let's see. You did not do this second one. Let's see if we can do that now. What's the probability you find a bad one within the first 10 that you examine? What's the probability you find a bad one within the first 10 that you examine? Okay, so there are actually 2 different ways to do this. And so I'm going to let you think about that for a second and see what you come up with. And then we'll see how that... How did you decide to do this one? Geometric what? Okay, so you thought that if you're going to find, hey guys, snap, if you're going to find a bad one somewhere within the first 10, it could be, you're interpreting that as it could be in the first spot, second spot, third spot, and so on. Is that how you interpreted that? Well, you can do that. You can say there should be the first bad one occurring somewhere in the first 10. So that .02 should occur in one of those places. All right? And so you could do that. I don't remember what that equals. But 18 what? Okay. 18.3. 0.29, yeah. Okay. So here you could also interpret it as this. If you find a bad one, that is really saying you find at least one bad one in there. And if you are finding at least one bad one in there, then that is 1 minus no bad ones, in the 10. So if none of the 10 are bad, then what does that mean they all are? Good. That means they are all good. So that means 1 minus the probability of all 10 of them being good. This also equals the same amount. Okay? So either way that you think of that, those are both okay processes. Just show one of those methods. Okay, let's do this one. For the basketball player in exercise 7, that's where he makes 80% of his shots. What's the expected number of shots until he misses one? How many do you expect to have to, he's standing there, how many do you think he's going to have to throw on average until he misses one? How do we figure that out? Do we know in? Do you know in? Do you know how many trials you're going to go to? Okay, you do not know in. You do not know in. Therefore, the expected has to be this. 1 out of P. 1 over P. All right, so then that will look like 1 over... Yes. No, until he misses... Oh, yeah. Point 2. That's correct. Good. And that comes out to be 5 shots. Make sure you label these, okay? Because you're going to have to sit there. So 5 shots. So you anticipate that 5th shot is going to be the miss on average. So make, miss. So this incorporates the 5th one will be that miss. Okay, let's look at the next one. For the computer chips described in exercise 8, how many do you expect to test before finding a bad one? So you need to find the bad one. Which one is that one going to be?
50th one.
How you get that? How is it the 50th?
Well, because you do 1 over 0.0.
Okay, very good. And so that means that you're going to find the bad one is the 50th. Okay? Be careful on the wording. If they say, how many good ones are there going to be? Then how many good ones are there going to be? There's 49 good ones. The 50th one is the bad one. The 50th one is the bad one, on average. Okay? All right. Very good. So what I want to do is stop right here for a minute. I'm going to pause the video, and I'm going to give you about 10 minutes to go through and do all of this number 11 and number 12A that you did not do yesterday, and I'm going to see how you do with that. We'll meet back here in a second and go through those. Correct, yes. Okay, so let's actually go through that ABC, and then let's kind of talk about D for a second. All right, you guys look up here. On average, how many donors do we check to find someone? How many are you gonna go until you get an AB donor? That's gonna be what? I got you do 1 over 0.04, which is, okay, so 25 donors on average. The 25th person is going to be the AB donor. Okay? On average, you're going to have to check 25 people to get one. All right, what's the probability that there is a type AB donor? So among the first 5, that means it could be anywhere placed in the first 5. That means the AB donor could be first, or the AB donor could be second, or, and so on. The AB donor could be third. This is the cumulating. This is cumulating all of these possibilities. If you go geometric PDF and the 0.04 is in the 5th spot, then you are doing, I'll show you, this piece only. If you do geometric PDF of 0.04 in the 5th spot, you are only doing this piece right here, which is 0.96 times 0.96 times 0.96 times 0.96 times 0.04. That's just the one case. Cumulative is what says, I want to see 0.04 in the first spot, or in the second spot, or in the third, or in the fourth, or in the fifth. So that will accumulate, and that's what this is doing it, because it can be anywhere amongst the first 5. So therefore, this is a geometric CDF anywhere amongst the first 5. And I don't know what that number is. What is it? 18.46%. Okay. Now here, with this, is the identical thing. Anywhere amongst the first 6. So it's the same. Geometric CDF of 0.04 amongst the 6, which is 21.7%. Okay, now with D, you kind of like think that this is another one of those geometric ones, okay? So let's look at this. What's the probability that we won't find a type AB donor before the 10th person? Let me draw a picture so you can understand better what this is saying. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's the 10 people. You are not going to get an AB donor before the 10th person. I don't care what you get in this 10th spot. It doesn't tell me that that 10th spot is an AB donor. All it says is that these 9 here are what? Are not an AB donor. So what's the probability that this is not, and this is not, and this is not, and this is not, and so on? So technically this is just 0.96 to the 9th power. Okay, now what did you want to do? What was it that you thought it was? The geometric CDF of 0.96, 9? Okay, so let's talk about what you just did. If you did geometric CDF of 0.969, is that what you did? And it comes up with the number 1. Here's what it does. This value means it's in the first spot, or it's in the second spot, or it's in the third spot, or, and so on. That's not what this problem says, because if that's what it is, you got an AB donor right there. This problem says you do not get an AB donor in the first 9. So all of these are 0.96s. Okay. All right. Very good. Okay. That's why the geometric CDF is not the correct function for this. Okay. All right. Let's move on. 12A, you did not do yesterday, and I think I didn't tell you that. you know, was having other issues. But I didn't want y'all to do 12A yesterday. Even though I had put day 1 on there, that was a boo-boo on my part, and I told all the other classes to not do it, but forgot about y'all. On average, how many men do you think the research is going to have to check to find that one that is colorblind? How's that going to look? Good, 1 over 0.08. So on average, 12 and a half men. Label it 12 and a half men. Okay, and remember, this is an average. He checked 11 guys and found the 11th one wasn't colorblind. I checked 12, or no, sorry, you checked 12 and the 12th one was. I checked 13 and the 13th was, because I stopped at the 13th, so that averaged out to 12 and a half men. Okay, that's an average. That's why it can be unrealistic. All right, let's see how you did on these on your homework. What's the probability she won't find anyone among the first 4 men? So all 4 of those are not colorblind. Next, what's the probability that the first colorblind man is the 6th? This one is saying exactly in the 6th place, particularly in the 6th place. It's not anywhere up to the 6th. Do you see the difference between among the first 6 means anywhere in the 6th? That's why you get cumulative. This one says is the 6th person. So that means it's only that case right there. It's geometric PDF. All right, and then here we have this one. What's the probability that she finds someone who is colorblind before checking the 10th man? So, how many did she check? She checked 9, so she had to find a colorblind person within the first 9. How's that going to look? Okay, you can go 2 different ways on how to do this. None. You can say, what's the probability that she finds someone before checking the 10th? So within the first 9, she's going to find someone. So she could find it on the first one, or she could find it on the second one, or she could find it on the third one, and so on. So geometric CDF, finding one somewhere within the first 9. Okay, that is one way that you can think of this problem. But another way, and the way that I used to think of it actually until this year, was this. She needs to find at least one amongst the first 9. So to find at least one is 1 minus the probability that none of the 9 are colorblind. And in order for none of the 9 to be colorblind, it's 1 minus, all of them are good to go, 0.92 to the 9th. These 2 answers come out to be the same probability. Okay, so either one of those ways, you can think of it that way. They both are essentially, at least one of them is colorblind. Okay, amongst the first 9. All right, let's finish this thing out. Here's number 13 is the lefties. You guys did 13A. Let's check it. So you have already done this one. The first lefty is the 5th person. So exactly in the 5th spot, there it is. Geometric PDF 0.13, 5. Exactly in the 5th spot. B, how you going to do this? There are some lefties among the 5 people. What you want to do on that one? Geometric CDF. So anywhere in there is sprinkled a lefty. You could also do it 1 minus the probability of none. There's at least one lefty in there. Okay, so write that down. In order for none of the 5 to be lefties, all of them are righties. So you can do that. Or what you get each one of those? They're the same. 0.2, what? Does it round? Okay. All right. That's a probability. Here is one, and you were to do this last night, but notice, it defines the order for two situations. It says you get a lefty in the second spot, or you get a lefty in the third spot. That's what this is saying. So how does it look for you to get a lefty in the second spot, a righty, and then a lefty? Yes. Or you get a righty, righty, lefty. So that is the way that can work. It happens in particular on the second one, so you could do PDF on the second spot plus PDF on the third spot. You actually cannot do if you did geometric to the third spot, what's wrong with that? It would include it happening on the first spot, and it's not supposed to happen in the first spot. Do you see that? You would go geometric, if you did this pure calculator, PDF 0.13 occurs in the second spot, plus geometric PDF 0.13 occurs in the third spot. You could do that. Okay, C is exactly 3 lefties sprinkled somewhere throughout that. That is a binomial problem. You have to do this by showing this work. This is a necessity. You have to show 5, choose 3, 0.13, and there are 3 of the lefties, 0.87, and there are 2 of the righties, and that's 1.66%. Here is how that would go into your calculator. Okay, so that work has to be shown, and then you can plop it in your calculator to get your answer. Okay, E and F is a cumulative binomial problem, and we're doing that tomorrow. So save those for tomorrow. All right. I want you to do 15 and I want you to do the rest of this page, 15, ABC, and 17A. I'm going to pause, let you do that, and then we'll check those real quick. Okay, there's you some hints there because all 5 of these things that you compute are straight up from the formula. Okay, so let's check those. You might have needed to double check on 17 that it was asking for right-handers. So your probability of success was 0.87 on that. Okay, so 15A, lefties was N times P, what, 0.65? P, men, these are men, I think, that you were checking. So on average, when you check 5, 0.65 of them were lefties, and how can that happen?
Average.
It's an average. Okay, Heath checked 5 and there were no lefties. Kristen checked 5 and there were no lefties. I checked 5, there was 1 lefty. That averages out to 0.6. Oh, that's 0.33. Sorry, I need to fix that. Y'all 2 got a lefty. I didn't. That's 0.67 of a lefty amongst our sets of 5. All right, what's what standard deviation? 0.75, 2, I think. Okay, 0.5752. This one here, 1 out of 0.13. What's that one? 7.692 or something like that. And these are men. You have to pick that many men. Now this is right-handers, so your probability of success is your 0.87. This one is 7 point what? Oh no, it's 10.44. I think, is that right? With what standard deviation?
1.16.
Okay, 1.16. All right, very good. Now, on the next one, there's only 2 more because this one here, B, is going to happen tomorrow, and so is D. So those two happen tomorrow. So real quickly, if you have that out of 12, they are not all right-handed, then that means at least one of them is lefty. And how do you do at least one? So there's two ways you could do this. You could also do this one with the geometric CDF, 0.13, 12. Okay, there's two ways to do that one, and then I'll leave part D up there. But your assignment is to do the 12 days of statistics, but you get to leave off 3 of them, so hold on. So 12 days of statistics, that's 12 problems. And you are going to omit for now day 5, 10, and 11. So you got, what, 9 problems? That's not bad. Okay, so 12 days of statistics, don't do day 5, 10, or